All right, so for the last speaker for our 24-hour group theory marathon is Arman Darbinyan from Texas A&M University, and he'll be telling us about computability properties of left and bi-orderable groups.
Thank you, Turbo, and thanks for inviting me to this innovative conference. And I apologize for these things that happened, technical part. Okay, so let's start. I would like to talk about computability properties of left and bi-orderable groups. And let me start from the basic definitions, which I believe most of you know. So first of all, it's we define the bi-orderability or left orderability on the group. So it's an order that is a linear order, so that in addition, in the case of left orderability, the order is invariant under left multiplication, and in the case of bi-orderability, it is invariant under simultaneously left and right multiplication, as it is given here by conditions 1 and 2. So one of the key concepts that is connected with these groups is positive con. And positive con is simply the set of all elements of the groups that are strictly larger than the unit element. So with the positive con, of course, there is this dual set, which is which one can say negative con is the set of inverses of positive elements. And the other concept that I would like to go into is the concept of computable groups. The group is called computable. So if there exists an enumeration of the group, so first of all, I would like to emphasize that when we consider computable groups, we consider the groups with a given enumeration. So once you describe the table of multiplication of the group, when the group elements are represented by their numbers, their indices, then this table of multiplication should be a computable table. So once this happens, then we say that the group is computable with respect to the given enumeration. It must be noted that there exist computable groups that are not computable with respect to some particular enumeration, which is natural, right? But there are also groups which are not computable with respect to any enumeration. So one can think about computable groups as a generalization of groups with decidable word problem, but not restricted to the case of finitely generated groups. So this class of groups includes also not necessarily finitely generated countable groups. And this concept was introduced by Rabin and Maltsev independently. So one in Soviet Union, Maltsev was working in Soviet Union and Rabin was working in USA, a student of Alonzo Church, by the way. And it was like part of a program of a so-called structural computability theory that was initiated by Froelich, Jefferson, and others, with the goal to study the interaction with the algebraic structures and computability theory. And in the same way we defined computable groups, in the context of this computability, computable structure theory, one can also define computable orders. So a given order on the group G is said to be computable if the following two properties take place. First of all, again, we define this property with respect to a particular enumeration of the group. And if at the same time, with respect to this enumeration, the group has the group is computable and the positive con is also computable, then it means by the definition, according to the definitions, that the order is a computable order. In other words, there exists an algorithm, so in layman's terminology, that for a given element of the group decides whether this element is a positive element, negative element, or is just equal to the trivial element. So one result that I would like to mention is the direction of interaction between orders on groups and computability properties is the very recent result of Antolin, Rivas, and Su that says that gives a complete classification of left orderable groups for which the left order is a regular language. So what I mean, or what this theorem means by regular language is the following. One can consider the positive con for the finitely generated groups as a formal language. Simply take all the finite words with respect to the given set of generators, finite set of generators, and these finite elements that represent positive elements with respect to the order, they define the language of positive con. And this result gives a complete characterization of when all the positive cons for a given group are regular languages. So it says that it's an if and only if condition with poly-Z-Tatarin groups. So I will not go into this definition, details of the definition of Tatarin group. So the formal definition is given here. It's a little bit technical, but one nice property of Tatarin groups is that they are solvable groups. So we'll return to solvable groups a little bit later. But now I'd like to define what it means that the group G is computably orderable. It simply means that it has an order that is computable. So if the order is bi-order, then we say it's bi-orderable, computably bi-orderable. If the order is left order, then we say that G is computably left orderable. And one natural question that could be asked about computably orderable groups is actually a question that was asked by Downey and Kurtz. Actually, here I would like also to mention that Downey and Kurtz were the first ones who systematically initiated the program of studying computability properties of orders on groups. It was in 1980s. And the questions that they formulated is as natural as it could be, which asks the following. Is every computable orderable group isomorphic to computably orderable group? So as you can see, it doesn't mention the word finitely generated, which means that the question also is appealing for computability theorists. So in group theory, especially geometric or combinatorial group theory, we like working with finitely generated groups. However, this question includes a broader class of groups, which are just countable groups. So not necessarily finitely generated. And the first answer to this question for a particular subclass of groups was a positive answer by Reed Salomon. It's a theorem that says that every bi-orderable computable abelian group possesses a presentation with computable bi-order. So once we are restricted to the class of abelian groups, then the answer to the question of Downey and Kurtz is positive. So now, in the context of finitely generated groups, of course, this result looks trivial because finitely generated abelian groups are kind of have very easy structure, especially from the computability theory perspective. But once we move from countable group to from finitely generated groups to countable groups, and of course there are different enumerations of the groups, which makes the structure, especially the link between the algebraic structure and the computability structure, much more complicated. However, still this theorem holds. And quite recently, in 2018, Harrison Trainer showed that in general, the answer to the question of Downey and Kurtz is negative for the class of left orderable groups. In particular, he constructed a left orderable countable group that does not possess a computable left order with respect to any presentation of G. However, the group is left orderable and computable. Though this leaves two natural questions unanswered. First question is, what about the class of finitely generated groups? Can we make the same kind of assertion? And the second, what about the bi-orderable case? So this is a negative answer for the class of left orderable groups, but not bi-orderable groups. And here I would like to advertise an answer to this question that was obtained 2 years after the result of Harrison Trainer, that says that there exists a two-generated bi-orderable computable group G that does not embed in any countable group with a computable left or by order. So it not only is a counterexample to this question of Downey and Kurtz, but it says that it doesn't even embed in a group that will have the properties in the question of Downey and Kurtz. And moreover, this group G can be chosen to be a solvable group of derived length string. So now this is this last session is interesting because it gives some nice algebraic structure on the group G that is a counterexample. And given the theorem of Reed-Solomon that I already mentioned, a natural question is the following. That again, I would like to advertise, and I think this is a very interesting question. So basically the question is what one can say about the question of Downey and Kurtz once one is restricted to the class of metabelian groups. Quite possibly the answer to this question is positive, and if so, then it will be a nice addition to the properties of metabelian groups that are not true anymore once we jump from the class 2 length 2 solvable groups to the length 3 solvable groups. For example, it's true that for finitely generated metabelian groups, the word problem is decidable, and even by Noskov's theorem, the conjugacy problem is decidable. However, these properties are not true anymore for solvable groups of derived length, finitely generated solvable groups of derived length 3, for which it's even known that there exist a continuum many pairwise non-quasi-isometric groups. So this will be a nice addition to this kind of properties that separate metabelian groups from solvable groups of derived length 3. The other type of results in these directions that I would like to mention is so-called finitization theorems. So what I mean by finitization theorem? Basically, the questions that I mentioned and the results that I mentioned above are results that are interesting in the context of computability theory and not only in the context of geometric group theory. By finitization theorems, I mean a cluster of theorems that bring the concepts from the computability theory into the context of geometric group theory. So one more time, I would like to emphasize that in geometric group theory, we say we are mostly interested about finitely generated groups. And in the context of computability theory, we can consider like arbitrary cardinality of the group. And finitization gives a link between the concepts that are defined in this particular case that I would like to discuss here, that are defined for countable groups, and it redefines them or translates them into the language of finitely generated groups. So the first theorem of this kind is a characterization of computable groups, which says that a computable group is computable if and only if it computably embeds into a finitely generated group with decidable word problem. computably embeds, it means that the image of the group with respect to this embedding is a subgroup of the large group for which the membership problem is decidable. In other words, again, in more informal terms, it would mean that the large group in algorithmic way remembers where the small group sits inside it. So it algorithmically remembers the position, the place of the smaller group that sits inside the large group. The other theorem of this kind, this finitization theorem, that I would like to mention is a characterization of computable orders. Again, it is done in the same manner. Namely, we have that countable group H has a computable left or by ordering, if and only if it computably embeds into a finitely generated group with computable left or by order respectively. So these two theorems, these two characterizations actually are quite similar. And one important feature of them is that they bring the concept from computability theory into a language that is understandable in the context of geometric group theory. And another result of this kind can be considered as a strengthening of the previous theorems that I already mentioned. It's a result that I obtained with the Marcus team book. It says that the countable group has computable left order if and only if it computably embeds into a finitely generated simple group with computable left order. So here, I would like to make a remark about finitely generated simple groups, that the existence of these groups was an open question for a long time. And actually the first examples of such groups were discovered by Hyde and Lotta in 2019, so quite recently. And it appeared to be that this class of groups is actually quite a broad class of groups, as the theorem, the mentioned theorem indicates. And finally, before finishing my talk, I would like to mention probably the most famous finitization theorem, at least in combinatorial group theory. That is the theorem of Boone, Hickman, and Richard Thompson. So I will tell what was the contribution of Richard Thompson. It says that a finitely generated group has decidable word problem if and only if it is a subgroup of a finitely generated simple subgroup of a finitely presented group. Now the part that this simple group is finitely generated, it is the contribution of Richard Thompson in a paper that was actually given the first applications of the Thompson's group V. Basically, in the result of Thompson, he used in a quite prolific way the concepts that he defined and then gave rise to the celebrated Thompson's group or Thompson's groups. It's a family of groups. And in this context, Bludov and Gloss showed that the similar theorem is true if one restricts to the class of left orderable groups. So, namely, it says that finitely generated group, a finitely generated left orderable group has decidable word problem if and only if it is a subgroup of a simple subgroup of a left orderable finitely presented group. Now, the theorem of Bludov and Gloss was missing the part that the simple group is finitely generated. And in this context, the natural questions that was actually formulated by Gloss in slightly different terms is the following: can one obtain a left orderable version of the theorem that is mentioned here? So, namely, can one also say that the simple subgroup is finitely generated? So, for the general case, this question is still open, but for the case when the group has recursively enumerable left orders, the answer is positive, as indicated by the following theorem that says that a countable group with recursively enumerable, not necessarily recursive, but recursively enumerable left order has computable left order if and only if it is a subgroup of a finitely generated simple subgroup of a finitely presented left orderable group. So I would like to stop here, and thanks for listening.
All right, let's thanks the speaker. Okay, so any questions for the speaker?
One.
Go ahead.
That last theorem, is the group in question Thompson group V?
In this theorem?
Yeah.
No, actually, to obtain this theorem, we use the concept of we use Thompson's group F, but it is used in a not straightforward way. Actually, we use the constructions that was recently invented by Roman Tessera, by Tristino and Mattebon, and it was actually a development of a construction that was even previously known by de Rohan. All three are French mathematicians, and actually it uses the concept of piecewise linear groups, but it uses in a different way. Actually, it gives we use a construction that is considering some homeomorphisms of a suspension space. So it is a two-dimensional manifold, unlike to the case of Thompson's group. So we use like homeomorphisms on a two-dimensional manifold, but locally the transformations that we consider, they look like the transformations of Thompson group. Namely, they are piecewise linear.
Because F is not simple. So
exactly, F is not simple, but in our theorem, it is very important that the derived subgroup of F is simple. So this is why we explicitly don't use the fact, we don't use Thompson's group, but somehow we squeeze this useful information from the Thompson group that is derived subgroup is simple. This is of key importance for us.
And the derived subgroup is not finitely generated.
It is not, and it is not a challenge on our way. And because of all these challenges, first of all, the question of existence of finitely generated simple left orderable group was a wide open question for around like 30 years. It was formulated by Remtula. This kind of restrictions make it very challenging because you keep one property, but you trade off with another property. So in order to combine all these properties, it is the main challenge of this kind of results.
Wow. Cool.
All right, any other questions? Well, if no, let's thank the speaker again.
Thank you.
Let me turn off the record.